electrochemical energy storage and conversion toward carbon neutrality. And I will chair this section. Our first speaker is Professor Zijian Zheng. And here, please allow me to give a brief introduction of Professor Zheng. Professor Zheng is currently a full professor at the School of Fashion and Textile, associate director of the Research Institute of Intelligent and Wearable Systems, lead investigator of Research Institute of Smart Energy at Hong Kong Polytechnic University. And his research interests include the surface and polymer science, nanofabrication, flexible and wearable electronics, energy storage, and conversion. Professor Zheng received his bachelor degree at Tsinghua University in 2003 and a PhD at the University of Cambridge in 2007. In 2008, he worked as a postdoc researcher with Professor Charles Marking at Northwestern University in USA. Now, he joined the Institute of Textile and Clothing as assistant professor at PolyU in 2009 and promoted to tenured associate professor in 2013 and professor in 2017. He has published many papers and including Science, Nature, Material, Nature Communication, and so on. And he also files over 25 patents and more than 15 academic awards. He serves as guest editor of Advanced Materials and Small, and currently he is editor-in-chief of EcoMatter, flagship open access journal in green energy and environment published by Wiley. He is elected the founding member of the Young Academy of Science of Hong Kong and Changjiang Chair Professor by the Ministry of Education of China and the Senior Research Fellow of UGC of Hong Kong. Now let's welcome Professor Zheng, please.
Professor Hi, thank you.
Yeah.
Thank you, Zheng Lao. Is my voice clear? Hello, is my voice clear?
Yeah, clear.
Okay. It's good. Okay. Yeah, and thank you very much for a kind introduction, and I thank organizer to invite me. I understand this is a part of a celebration of 85th anniversary of the Hong Kong PolyU. So today I want to talk about something that we've been developing, I will say in the last about 5 years, publication-wise in the last 4 years, how to make a really flexible and we try our best to improve the performance of flexible batteries. So I'll give a change of title a little bit, but then I think the focus of the talk will still be the same about this textile composite electrodes for wearable batteries and beyond. So my group has been working a lot on developing new materials and device form factors and flexible batteries for flexible and wearable electronics in the last about 10 years. I show you quite a bit of application scenario where this electronics can be worn outside the body. And for wearable electronic, I think in a bigger scope includes those devices can also be implanted under your skin, inside your body, or even inside your vessels. So it's quite a wide variety of things they can think of and explore. In our research institute now has been renamed and promoted to an independent school of fashion and textiles. Of course, we emphasize a lot of how to make use of this fibrous type of materials, textile in general, and this engineering toward flexible electronics. At least on the left-hand side, that many devices and functions that we've been interested in, and many other people have been interested in for wearable applications. I highlight a battery because today I'm going to talk about it. And you'll see for all the sensors, communications, and then actuators, etc., you do need a power system and most likely to be a rechargeable battery. If you want to put things into this kind of a nice format, it will require in certain way that the device or the materials should be intrinsically or structurally lightweight, flexible, and stretchable, and that allows drapability, biocompatibility, permeability, integratability, and durability during the wear. some of the new concept also include this self-healing ability in recent years. Now, I want to show you some very old picture though. This is a picture that I grabbed from the internet about 7, 8 years ago. I was saying this picture has been existing there for about 10 years. You can tell from, for example, in the middle of this Google Glass and this iWatch, it's almost like generation 1 product. If you think about now, after so many years, the iWatch now, I think it's Gen 6 or Gen 7. Sorry, I don't have one, but I think it's at Gen 6 or Gen 7 iWatch. They don't look that much of a difference, right? So basically, all the wearable electronics or products nowadays are made of rigid parts, chips and components, everything together, and then surrounding or linked with a kind of, for example, a rubber band, a fabric, something like that for wear purpose. And so we start to think about why is this, right? And you think about this advanced electronic, for example, foldable phone. The OLED has been really flexible or even foldable. This flexible circuit board has been really, really flexible in recent years. The antenna that we use a lot can be very, very flexible as well. So what hinders this kind of a product design? I think at the end of the day, it's because of the battery. You will see that all the things here, you don't really see the best power supply, but the batteries are either embedded in the electronic parts, or you require an external cable to link to the power source, right? So this has been what we've been using the last 10 years also. So there actually a strong need for the development of very, very flexible batteries, which allow you to go to the next level wearables that will enable a seamless type of integration between the flexible electronic part and the flexible kind of a power supply part. And at the end of the day, the entire product or system level, everything will look very, very flexible or perform in a flexible manner. I give a kind of a requirement chart over here in terms of the energy density per volume and strength level. Now, energy density, I think everybody got it because this is energy symposium. Strength is typically a material representative of how flexible your material or how flexible a device is going to be. So according to this printed circuit institute, typically if you want to name something a flexible electronic, the material inside should at least be able to overcome a strength of 5%, the 5% of deformation of its original size. Now, where we are here over at the bottom, at the bottom right corner, that means that our rigid or commercially available lithium-ion batteries, which is rigid, can fit most of the energy needs. They're energy dense, okay? The stability is pretty good. The problem is, however, they are not flexible at all. So the strength level is well below 1%. They hardly be bent. In the recent couple of years, there are quite a bit of development in the industry where they try to engineer the technology that we're being using in a conventional battery system and then convert it into a flexible type of a lithium-ion battery. And the result is okay, but it's not that exciting because you see that there's a huge sacrifice of the energy density. And what you gain is a little bit of the strength, that means flexibility, but then it's not to the level where it is expected, right? So obviously you want to push this number from the bottom left to the top right corner. So to enable a high energy density and highly flexible type of batteries for different kind of applications. So why the lithium-ion battery technology nowadays we use are not suitable for flexible applications? And one of the major reasons because of the use of this metal foil as a key component for current collector applications, right? So aluminum foil and copper foil, these are quite bendable, right? That's what being used in the lab, like a 6 to about 50 micron thick. But the fatigue of this metal is seriously an issue. All these metals has a very low yield strength, about 1%. And once your deformation is over 1%, right? In most of the cases, when we flex our cells, the deformation will be well over 2% actually. So the material will go to a plastic deformation regime, meaning that if you stretch it, they will become thinner and thinner and thinner. And this process is irreversible, so they cannot come back. So what's the end of the phase, right? So if the material is getting thin and thin, they will crack, they will break, they will fracture. And this is what has been shown in this experiments in this video clip, where a student is actually folding or bending a piece of copper foil being in the lab. And then you'll see that it's getting thinner because you see the siege, and then there's a crack and breaking start. And once this crack start to propagate, easily one piece of foil will become two pieces, right? And this is a material properties that will be extremely difficult, if it's not impossible, to overcome if we really want to use the material. So make things short, I think I'll tell you that what I want to talk about today is that this textile composite electrodes that we've been developing in the last 5 to 6 years, where we try to replace this metal foil with metallic textile, which I'll show you later, that we've been developing in the lab. And then we coat the electrode material, either it's new material or commercial development material, on top of this 3-dimensional porous conductive fabrics. And since the fabrics always has some porous structure, right, roughly about 67%, the electrode material the slurry will penetrate to the pores and form a 3-dimensional interpenetrative composite like a material, right? So that's why we call it a textile composite electrodes. And what we found is that this kind of composite electrode, naturally, it is extremely flexible. It can go over tens of or hundreds of thousands of bending cycle without seeing an obvious decrease of property. We later also find out that we can actually engineer all the structures, all the components to improve the rate performance, that meaning the high speed of charge and discharge. To some extent, we also found that amazingly, it can also suppress dendrite formation. And that will be great for this type of metal application. Now, before I show you the detail about how each component made, I just want to show you in principle how this concept look like. Now, this textile composite electrode, basically we need to make a metallic textile in the first case. So we deposited a whatever base substrate it is, and it varies, or made of textiles, and then with intended some kind of a metal, for example, nickel for the cathode current collector and copper for the anode current collector, and on top of which we coat the cathode and anode slurries, okay, and then assemble a flexible cell. And the cell looks typical like this. This flexible pouch looks like similar to what we have in this pouch cell assembly. And you'll see that this video clips show you that how flexible the cell that we can produce, right? So this is a kind of a cell at a size of roughly about 5 centimeter by 3.5 centimeter. And then this is one single electrode cell, and then you can simply fold it, or you can crumble it as you want, right? And then this cell can safely cycle for about 500 cycles, as you see here. This was a cell that we produced a couple of years ago. Now, let me show you a little bit detail about how we really make all this. We make a metal deposition on textile for more than 10 years. It was very difficult to make at the very beginning. And the reason being that the textile material we've been using, either as carbon or polymer-based material, has a huge difference from metal in terms of the spinning energy, in terms of the thermal conductivity, thermal expansion, in terms of the mechanical modulus. They are of difference in terms of like a 1,000 or 10 of 1,000 difference. So in terms of structure, fiber is 3-dimensional. And fabrics and yarns are also 3-dimensional. They are very rough. The surface is not uniform. Sometimes they're a little bit dirty, right? Because they trap lots of particles. So it will be very difficult using clean room type of technology, for example, vacuum deposition, or even using like a new printing tool to make this metal deposition on the textile surface. So luckily is that we've been working on a technology, we call it a polymer metal deposition, so PEM in short, which allow us to deposit metal from the bottom up in a chemically reductive environment. So what we did was that, and we started this research about 13 years ago. What we did was that we first modified the surface with this thin layer polymer, which is designed in a way that allows absorption of inorganic salts or nanoparticles, if you want. And then this moieties is allowed, it's designed in a way that you will assist the subsequent metal deposition. Or of course, we can do metal oxide deposition or of other material as well, but then in this case, we do electrolysis deposition of metal. We've been working on this for more than a decade, so we can come up with lots of chemistry. I don't have time to go through detail, but basically, is that we can make the polymer synthesis, grafting as well. At the very beginning, about 13 in 2 hours, and now we can do that in about 15 seconds. And we can deposit with a good control the thickness and conductivity of the metal from around 100 nanometers all the way down to about 1.5 micrometers. And we can do that in many substrates. If we combine with printing tools, we can make patterns, right? Therefore, of course, we can apply to many devices, including the battery. Now, these are the metallic textiles of what we made. There's a 300 nanometer thick of copper that's deposited on top of commercially available cotton. Yarns, and this is fabrics, but no matter how it deposited, actually the surface of each fiber is nicely coated with a layer of metal, and it's dense, it's conductive, and it's highly adhesive. So we can go through a ATCC standard of washing, put it in a laundry machine and laundry for 40 minutes and dry, etc., etc. It was 30 times, and nowadays in our lab we can do 100 times for some substrates. So the adhesion is massive, and we are working on a paper to explain that. Hopefully, it can be accepted maybe this year. Now, let me go to one paper in detail to show you that how we actually make it and how does the composite electrode look like. And then I'm going to show you a bit more how to engineer the different structural material to improve the battery. This paper is actually the first paper we published for flexible type battery. And we make on a lithium sulfur system. So on the anode side, we make use of copper as a current collector, and copper coated onto the carbon fabric. On the cathode side, we deposit nickel onto carbon fabric and use that current collector. The reason is because the copper has a natural surface of oxide, and it has a high affinity to lithium metal, and therefore the deposition of lithium metal is pretty smooth. Nickel one has a catalytic effect for the polysulfide, and therefore it can improve the efficiency and then speed. All right. So this is how the lithium metal composite anode look like. Okay, nowadays there are many similar publications showing with similar images. So basically, in the cross section, you'll see a hundreds of thousands of fibers, and each of the fiber is conductive. It was coated with lithium metal, either thick or thin. And what we found through the experiment, and also I show you the result here of our simulation, is that when you actually bend this composite, which is on the left-hand side, you don't really see a high level of a strength or stress localization, right? So you do see something, but it's not high. If you compare to the one on the very right-hand side, at least the metal one, if you do the same experiment in the simulation, in the same condition, you see there's a huge concentration of force. And once this concentration is there, they will form a crack very easily. So, and then therefore, the lithium metal will fracture at the end. Okay, for the composite one, even though you do have some concentration, they don't actually fracture or crack. We also extract the data and then see what's the pure lithium metal look like. You will see that the similar result, that you do have some stress. It's not high. It's not high enough to induce a fracture. Okay, there may be some tiny cracks, but not enough to induce fracture. So this is mechanical flexible. Electrochemically, it's quite stable. If you see the over potential, right, the red curve is our sample that enable a long-term stability. And what you see from the microscope is that the electron microscope is that at the very beginning, right over here, about one cycle, you still see a like a clump or chunk of lithium metal, which most likely we don't like it, right? Because that's easily initiate some dendrite formation at the beginning. But as you cycle for 100 cycle, that's somewhere around over here, we don't really see any non-uniform type of aggregates or big chunk of lithium metal. Instead, we see every single fiber is well coated and uniformly coated with a layer of lithium metal. And on top of the entire electrode was coated with a layer of lithium metal. Okay, and this, we just use a needle to poke it through so that we can see what's happening underneath. And that tells you that if you compare with all this overpotential characteristic, it tells us that this structure helps us to stabilize the lithium metal and prevent the dendrite formation in most cases. If you compare to the lithium foil and lithium metal deposition on top of foil, there's huge dendrite formation and instability over the cycling process. So we were very happy at that time, right? Because we didn't do too much of experiment, and we observed this phenomena. We do the same trick on the cathode side, and then you see that again, each of the fiber was coated with a sulfur species, and the result is that we can enable a high rate of redox of the sulfur and also a long-term stability. I'm not going to the detail of the data analysis, but basically the nickel will help a lot in terms of catalyzing the redox reaction. So at that time, we demonstrate if you assemble these two pieces together, and then you can get a decent cell with a very little amount of lithium metal on the anode. We fix it at 6 milliampere hour per centimeter. Sulfur loading varies, so the DOD is actually quite deep if you think about this paper was published in 2018. And then therefore the energy density in terms of the stability at this energy density and the flexibility, it was pretty good and surprisingly good, I would say, to us. And if you think it more carefully, we're working with lithium metal, right? And this is lithium metal itself already has a yield strength of less than 1%. So we actually go to the most difficult question probably at the very beginning. And therefore, later on, when we change to different system or different material, we find it actually it's quite easy if it's just make use of what had been building up with the lithium metal anode. So there's a couple of clips showing you that how flexible it can be, right? And so you can bend this lithium metal, right? You can bend it, you can sort of fold it, you can hammer it, it's no problem, and you can cut it. And when we cut this cell, which is made of the used liquid electrolyte in the air, number one, we don't see a thermal runaway, overheating, and then we didn't observe any leakage of liquid electrolyte, which is kind of surprising to me as well. And we believe this is something related to this textile composite structure, where it actually can grab some of the liquids because of their structure. So later on, we want to challenge a little bit of the flexibility, all right? So what we find out is that lithium metal, indeed, you can't really fold it in a certain way. You can fold it a couple of tens of times, and then the cell probably will decay rapidly. But then if you just use commercial materials, and then you can adjust the slurries, and most importantly, if we can make some nanostructures on the metal deposition, in our case, we make some nano needle-like structures. You can improve the electrochemical surface area. You can also increase significantly the adhesion between the active materials and the surface and the current collector, and so that we can push the flexibility to the extreme, right? So this is the same clip as I showed you at the very beginning, that we can actually fold the cell. And at the same time, you'll see that using our nano, that's the N one, we can actually increase the speed significantly, right? The 10 Cs, we still get around 50% of the capacity of the electrode. And this curve show you that after 1,000 times of bending and not bending, right? The charge and discharge curve will heavily overlap, right? So that means how stable the cell it can be. We also try to improve a little bit of the, this stability of the anode, because I In the morning, we have a few speakers already tell us how important to suppress the dendrite formation, and then so that to improve the stability. There are many strategies of doing that. In our flexible type of composite lecture, what we found is there's one very easy way to do that, just using existing material and existing setup. But instead of putting our lithium metal next to the separator, we flip it around, right? So then at this point, the lithium metal is away from the separator, and in the middle, there's a spacer made of this highly porous, three-dimensional conductive textiles. What we found is that, and also like a Cui Yi in his earlier publication also found that if you do put down a little bit of these 3D conductive skeletons, it can effectively prevent the growth of lithium dendrite. Okay, that's number one. Number two, what we found in this electrical field, when you actually plating the lithium metal from a cathode to anode, then the lithium deposition will occur at the bottom. Okay, so that it does not really occur next to a separator. So therefore, even though there's tiny bit of dendrites, they don't first in contact with the separator, they don't really penetrate, they don't short the separator. So this experiment was very easy. You just do the same thing that I showed you in the lithium in the Nature Communication paper, and just flip it around and then assemble the cell. So what you observe is in this inverted structure at the bottom, we don't really see lithium metal deposition and form dendrites. You do see an expansion of lithium metal, very little, right? And that's normal. But if you see on the up one, the upright structure, which is normal one, you do see a huge amount of dendrite formation under a very, very short period of time. Okay, so I think this come up with a nice example, and then we use that to run a cell in a very long cycle. So this is 750 cycles of lithium metal running, and it was quite successful in a ECDMC, a commercial electrolyte, a capacity retention which is about 99.98%. Now we can make it flexible, and that the previous one, this one is not flexible. Okay, we make it flexible, and then we find that if you really want to make it flexible and stable, just evaporate a thin layer of gold before you deposit the lithium metal. So again, this is kind of a quick trick we found. We evaporated one layer of gold on one side of the carbon fabric and deposit lithium metal on that side and flip it over and do the exact same experiment. And you observe almost the same kind of electrochemical phenomenon. Okay, but then the cell is quite flexible when you flex it. Okay, so I think again, this is just some tricks that we learn and I would like to share. Apart from that, I think we also concerned quite a bit in terms of how can you really do that in a large quantity, and we have been challenged by our communities a lot. They're saying that this kind of applied research, and if you really want to make the flexible battery, you need to coat it in a very fast way, right? So for the graphite or silicon anode, we can always do the same slurry coating. That's no problem. But with lithium metal, the coating nowadays we're using electrochemical deposition, and it takes hours, right? We can do some melting, but then again that takes quite a tens of minutes, okay, to wet a very tiny surface. So what we found is that we can learn from a textile which wick sweat, and use that analogy to develop metallic textiles as a current collector that can wick molten lithium, right? So our sweat can be wicked by fabric in less than a second, and therefore which allow it to evaporate very quickly and dry quickly. So in our case, we also design a current collector in a similar way and with a similar structure, but coated with, of course, metals and then cuprous oxide, which has a high affinity with lithium. And then we contact this lithium on one end, and this stuff can be wicked, the molten lithium can be wicked into these current collectors extremely rapidly, right? So you see this time is 0.6 second, right? That's 600 milliseconds. I show you two video clips. On the left-hand side, this is a video clip showing the wicking process that is being slowed down by 50 times. So if you see this unit is millisecond. So already at 20 millisecond, the half size of the current collector has been fully wicked with lithium metal. And when you reach about 50, 60 milliseconds, the entire sample, this is about 3 millimeter long sample, has been fully wicked. So we believe in the future we'll be able to use similar technology to make a very high speed of fabrication. And this speed is already about 10 meters per minute, which is far over the battery coating speed. And once you get it, it's a big sample that's showing that how flexible it is. On the cathode side, sulfur cathode, of course, we also have a big headache because we need to coat a thick sulfur on top of the current collector, right? And normally what we get is that if you buy from market, a thick one always perform very poorly. It will give you a 700 milliampere hour per gram, something like that, or 800. That means thick sulfur does not give you good performance. For those papers who publish many strategies to coat thick sulfur, it typically, again, takes very long time. So we think, can we actually, again, engineer something so that we'll be able to coat the sulfur as we coat a normal slurry on top of current collector and still achieve a very high capacity, right? So we did that, and what we found is just simply we just need to control the evaporation rate, the viscosity, and so that we can control the formation of a mosaic-like, it's just like what we have in the kitchen or in the toilet, those mosaic structure, a mosaic like a sulfur. And this can be done very easily on our metallic textiles, because during the wet drying process, this liquid film will be somehow pinned on the protrusions of each woven structures, and the pin area will form a thicker sulfur. The unpinned area will form more like that deep cracks, right, and generate this kind of structure. And it looks like this, right? So, excuse me, I think somebody is not unmuting the microphone, right? So we'll look. It will look like this, okay? And then what we get is that even at a very thick electrode, we still get a very nice and decent capacity. You see that at this over 6 milligram, you get about 1,000 milliampere hour, right? A milliampere hour per milligram. So this is pretty high considering the electrode is extremely thick. Of course, not all the cracks will work. If we crack it in a way of as normal without control, I mean, you don't really see actually any good results. And the reason is because of their abnormal and irregular expansion and create extra cracks. And what we found is that this cracks is actually good for flexibility, right? Because and the entire sulfur electrodes already has been chopped up into mosaic pieces, and therefore you can when the entire electrodes bend, it's the bending stress can be released easily on the preformed cracks, and therefore there's no extra new cracks are generated, right, during this bending process. So in our dynamic bending or in ex situ bending, we don't see any issues about this battery stability. I will show you a couple of quick slides about how do we actually expand the TCE concept to other materials. For example, we collaborated with Professor Dan Wang in Chinese Academy of Sciences, and then we make use of the material, the vanadium oxide hollow multi-shell spheres that they develop, and then they extend their stability significantly. The problem of this shell is that the stability is not that good after they publish a Nature Energy paper, and so we will be able to address that issue a little bit. On the other hand, we do this anode with silicon, and this is being used for lithium-ion battery or dual-ion battery a lot. And again, the problem is similar. The silicon anode will crack, and then they will delaminate from the current collectors, and therefore we use our Tesla composite concept to also to address this issue. At the same time, bring additional flexibility to the entire entire cell. And recently, we just changed a little bit about the structure of the current collector from a fabric type to a yarn type. So we use the same technology, so we can wick lithium metals onto a yarn and form a composite like a yarn type of structure, and so that you can form a wire type of batteries. We can also expand this to supercapacitor. I'm not going to talk about in detail. One thing I want to mention is that this is something that can be actually applied beyond the flexibility, beyond the flexible battery. So in this case, I show you that we can also do sodium battery. We can also do sodium metal. It's not for flexible application. You can use it for that, but when we aim for high energy density grid application, and sodium is green. There's a large quantity of sodium. It's cheap. Eco-friendly for manufacturing and recycling. The problem, obviously, sodium is not as stable as lithium. They don't have a high capacity as lithium. So by the DOE, it was calculated that if you want to overcome this commercial availability comparable to lithium battery, the energy density of sodium battery should reach somewhere around 200 watt-hour per kilogram, which is huge effort to reach, right? So in our case, what we found is that there's an interface made of nickel antimony, so NISB, that can stabilize the sodium metal significantly by forming this so-called heterojunction-like structure. And once you form this heterojunction-like structure, the deposition of sodium metal, will go to a competing structure where first the sodium will deposit it onto this island like a sodium antimony, and then they will deposit on the nickel surface because the nickel is more conductive electrically, right? So they will compete and self-smooth, and at the end of a deposition, they will form a very, very smooth anode, okay? And we don't really see a dendrite formation. Then we just use whatever I tell you in the previous slides, and by wicking this onto a three-dimensional structure, and we can make a sodium metal composite anode, right? And what we observe exactly the same what we observe in the lithium case. It's highly flexible, even though we don't really use it for flexibility application. It's highly flexible. It has a much better improved chromatic efficiency. It has a very low over potential during plating and stripping. The cyclone stability is way higher, and at high rate still performs similarly. So in this sense, we can use a very stable anode and then pair with a very thick cathode. The cathode is 7 million ampere per centimeter square. So we can build a very, very high energy cell. And this cell, if you calculate it with everything, is over 200 watt-hour per kilogram. If we use less electrolyte, we use a lean electrolyte, and of course we sacrifice the cycling stability a little bit, we can reach about 230 watt-hour per kilogram. And we believe this is one of the very best data when we publish a paper that actually do overcome this 200 watt-hour per kilogram kind of a threshold. Okay, so this is what we have right now. And I'm going to skip this. And what we have right now is that show you that the textile composite electrode, we believe is there lots of fun. It looks like it's quite promising to make our battery extremely flexible. The cycle life is not too bad. We can engineering the structure and the microstructure and the mesostructure, and then the materials to improve the stability to at least 500 cycles, no problem. Safety looks like there's some advantages. Number one, you can suppress dendrite formation. In our lab, we don't really see too much of dendrites. Number two, it can actually somehow hold electrolyte and does not allow it to leak out. The manufacturing ability, we tested a little bit and showed that it probably is promising to achieve a similar speed of manufacturing as we do in the battery industry. The rate performance is pretty good because the three-dimensional structure. still now, I think in this field, the problem is the energy density. The energy density in whatever reports so far, there's no single report showing a better battery in comparison to the rigid type of counterparts, meaning that you have to sacrifice quite a bit of energy density in order to reach a certain level of flexibility. And this cell is not any better than our existing lithium-ion battery that we use in the cell phone or in the laptop. I want to show you this last slide, a little bit hope that now we'll be able to make some flexible, extremely flexible and foldable, actually, lithium-ion batteries that can cycle very many cycles, that has a higher energy density in terms of weight, in terms of volume. They are all better than the we use commercial ones. And the flexibility is superb. So this cell is actually charging up the cell phone, okay, during the cycling of bending. Okay, so I think without further ado, I would like to thank my students and postdoc that contribute significantly to this talk, and also my collaborators that contribute to all the papers that I show you, and funding agencies. Thank you very much.
Thank you very much, Professor Zhou. Now let's go to the Q&A section. Because of time, maybe we can only ask one question. So any question from the audience? You can tap in the chat box or directly unmute to ask. Okay, seems no more question. Thank you very much again,